Today we're going to start Unit 2. We're going to learn electron configuration and nuclear chemistry. And today, on day 1, you're going to learn the quantum mechanical model of the atom and be able to write electron configurations. So let's do a review of the Bohr model, which we went over previously. The Bohr model, remember, has your valence electrons in the outermost energy level of an atom, and the octet rule states that atoms tend to react to achieve 8 electrons in their valence shell. So remember, your valence wants to have 8. Atoms with 8 valence electrons are exceptionally stable. Remember, your noble gases on the very end of the periodic table, 8A, or group 18, have a full valence electron shell, which means that they are stable. The Bohr model of the atom is not complete and is no longer used as the model of the atom. There's substantial evidence that indicates that electrons do not move around the nucleus in perfect circular orbits. So even though we draw it with the nucleus in the center and the electrons going around it, they actually kind of go around in a three-dimensional cloud.
The cores of atoms tend to stick together, but electrons are free to move. And this is why chemists love electrons. If we could marry them, we probably would. But electrons are weird. They appear to behave either as particles, like little baseballs, or as waves, like water waves, depending on the experiment that we perform.
So through the work of Max Planck, Albert Einstein, Louis de Broglie, Arthur Compton, Niels Bohr, and many others, current scientific theory holds that all particles also have a wave nature, and vice versa. This was proved through wave-particle duality, which is the concept that every elementary particle, like an electron, is described in terms of not only particles, but also of waves. The limitations of the Bohr model, which we previously learned, is that scientific changed our understandings of what electrons really are. This created the need for a new model of the atom, which included the wave-particle properties of electron. The Heisenberg uncertainty principle states that it's impossible to know precisely both the velocity and position of a particle at the same time. This basically means that there's a fundamental limit on how much we can know about where an electron is and where it's going at the same time. So as you watch this next video clip, pay close attention to how the location of an electron is represented. Be prepared to complete a vocabulary entry for orbital.
One of the weirdest things about electrons is that we can't exactly say where they are. It's not that we don't have the equipment, it's that this uncertainty is part of our model of the electron. So we can't pinpoint them. Fine. But we can say there's a certain probability of finding an electron in a given space around the nucleus. And that means that we can ask the following question. If we drew a shape around the nucleus such that we would be 95% sure of finding a given electron within that shape, what would it look like? Here are a few of these shapes. Chemists call them orbitals, and what each one looks like depends on, among other things, how much energy it has.
So our current model is known as the quantum mechanical model of the atom, where you have these 3D shapes going around. The atomic orbitals represent the three-dimensional region around a nucleus where an electron is likely to be 95% of the time. This region is an atomic orbital, which is an electron's probable location. Probable because electrons have wave-particle duality. We can't know exactly where they are and what they're doing at the same time. Principal energy levels are the atom's major energy levels. The period an element is in on the periodic table tells you the number of energy levels. The outermost energy level is where the valence electrons are found. So period 1 has energy level 1, 2 has energy level 2, and 3 has energy level 3. The 4 energy sublevels, which make up energy levels, are S, P, D, and F. The sublevels had different shapes, which allow electrons to orbit the nucleus without running into each other. They always fill up in this order, S, P, D, then F. The S sublevel has only one orbital per energy level. Each orbital can hold a maximum of 2 electrons. So the S sublevels can always hold a maximum of 2 electrons. The S sublevel has a shape of a sphere centered around the nucleus. The P sublevel has 3 orbitals per energy level. Each orbital can hold a maximum of 2, so that means that the P sublevels can always hold a maximum of 6 electrons. Each of the 3 P sublevels are in the shape of a dumbbell centered around the nucleus, oriented in different directions. So similar to a three-dimensional graph, you have your Y axis, your X axis, and then your z-axis. All of these are 90 degrees apart. And these can be drawn the same way. You have your x-axis, your y-axis, and your z-axis. Your d sublevel has 5 orbitals per energy level. Remember, it can hold a maximum of 2, so that means the d sublevels can always hold a maximum of 10 electrons. The d sublevels have different orientations. You don't need to know them, but this is what they look like. And altogether, you have this cool looking starburst shape. The f sublevel has 7 orbitals per energy level. And since each one can only hold 2 electrons, that means that the f sublevels always hold a maximum of 14 electrons. And here's the diagrams for what the f sublevels would look like. So altogether, you have kind of a pyramid of orbitals. You can see the different shapes put together, and the different shapes put together will create your atom looking like this one. So to summarize it, the number of orbitals in your s sublevel is 1. It's the sphere, and it has a maximum of 2 electrons. Your p has 3 orbitals with a maximum of 6 electrons. Your d sublevel has 5 orbitals, and that means it can have 10 electrons, and your f sublevel has 7 orbitals, meaning it can have 14 electrons. If you have 1 energy level, that means that it can only have an s sublevel, meaning it only has 2 electrons present. If you have 2 energy levels, that means you can have both s and p, meaning you have 2 plus 6 equals 8 electrons. If you have 3 sublevels, that means that you can have s, p, and d. So you have 2 plus 6 plus 10 equals 18 total electrons. If you have 4 energy levels, that means you have all 4, s, p, d, and f. So 2 plus 6 plus 10 plus 14 equals 32 total electrons. This is known as electron configuration, which is the arrangement of electrons in an atom. Low energy arrangements are more stable than high energy arrangements. The most stable, lowest energy arrangement of the electrons in atoms of an element is called the element's ground state electron configuration. The Aufbau principle states that each electron occupies the lowest energy orbital available. So if you have 1s, 2s, 2p, and 3s, then you want to put your first electron here on your 1s. The second electron doesn't go in 2s, it actually goes still on 1s. If you've got 3 electrons, then you would move to 2s. But if you have 4 electrons, you wouldn't move to 2p yet. You would fill in the second spot available on the 2s location. Then you would move to 2p, so on, and then you would fill 3s. So you just you can actually see this on the periodic table. It shows us where each element's last valence electron is added in the ground state. On your new periodic table, go ahead and outline the blocks that make up S block, P block, D block, and F block. So here, work with you on it. So your S block is over here with your alkali and alkali earth metals. Your P group is over here with your noble gases and halogens. Your D group is right here in the center with your transition metals. And the F group is your lanthanide and actinide series. So in this example, you can see helium. Helium has 1s2, so its 2 electrons go in the 1s, and you have to fill out your energy level, so it has 2 total electrons. The next element, which is on period 2, group 1A, is lithium, and it has 3 electrons. So you fill out your first level, 1, 2, then 3 goes in your 2s group. Beryllium has 4 electrons, so you'd fill it out on your second group. Boron has 5, so you start filling in your second p level. Carbon has 6, add another one. Nitrogen has 7, add one more. Oxygen has 8. Fluorine has 9. Neon has 10. It follows your octet rule because it has all 8 electrons in your valence shell. Then you go back over to sodium, which is the start of period 3, group 1A, and add your first electron. Next one's magnesium. Add your second electron. Start 3p, which is aluminum, silicon, phosphorus, sulfur, chlorine, and argon, which is your noble gas. So you're really just following across the periodic table. Then we start back over. We go back to the beginning of your periodic table, and you fill out your 4s group. Remember, it's in the fourth period, group 1a, 4s. Then add the second electron for calcium. Scandium is where you're going to start your 3d, and that's your transition metals. And as you go across, you add all the electrons for those metals as well. And then at zinc, you've filled out your 3d10. So you go to gallium, which is your 4p. And it keeps following across until you reach krypton, which is your noble gas at the very end, 4p6. And you go back to the beginning, and you go back to rubidium, which is period 5, group 1a, and keep going across. Strontium, iridium, zirconium, and so on. Notice how long this looks. There is a way to abbreviate it, which we're going to learn next. So looking at our electronic configuration and our periodic table, it looks identical. You start with 1s and go across, 2s, go across, to 2p1, 3s, to 3p, 4s, to 3d, to 4p, 5s, to 4d, to 5p, and so on. Notice that you go from 4s to 3d back to 4p. And same thing, 5s to 4d back to 5p. Keep that in mind whenever you write out your electronic configurations. All right, so let's go ahead and practice. Oxygen is 1s2, 2s2, and 2p4. Aluminum is 1s2, 2s2, 2p6, 3s2, and 3p1. Iron is going to be 1s2, 2s2, 2p6, 3s2, 3p6. Start back over. We're going to go to 4s2 and then 3d6. Don't forget, after you fill out your 4s2, you go back down to 3d6. Bromine is going to be 1s2, 2s2, 2p6, 3s2, 3p6. Start back over to 4s2, 3d10, and 4p5. Don't forget, you go from 4s2 to 3d10 to 4p5. Strontium, which is in the fifth period, is going to start off at 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and 5s2. Nitrogen is going to be 1s2, 2s2, and 2p3.